the screen is visible and I'm also audible.
Yes, Aniket.
Yeah.
Both are working.
Okay, both are working. Okay. So what I was thinking is I would just give a brief recap of what Sir has done this whole week. You guys have seen the videos, I think. I can't do the proofs in the 1 hour tutorial sessions, but I'll try to cover as much as possible. And if you guys have any doubt in the proofs of the, I think Sir has said regret minimization and pack bound, and Sir has mentioned median uh, elimination algorithm, and Sir gave a brief description about Thompson sampling. So if you guys have doubt in any of those, uh, you can ask me as I start to explain each and every of this algorithm. I hope that is fine. Okay, so first I'll go through the UCB bomb. So it's known as UCB or UCB1, any way you can call it. So this is known as upper confidence. So it's an upper confidence bound algorithm. So the basic setting is you have, so this is a algorithm for multiple arm bandits. So I hope you guys are now familiar with the concept of multiple arm bandits and what you have. Like you have arms, each and every time you pull an action, the arms have an underlying unknown distribution. Distribution is unknown to you. So from that distribution, and reward is sampled, and you get a reward at each time. You want to maximize. Sorry. I hope my screen is visible now. Sorry. Yeah, so it gives you a random reward at each time instance t, and then what you want to do is you want to optimize. You want to minimize the regret that you get at each. Like you want to minimize the regret. So what you want to optimally do is you want to always pull the arm which has the maximum expected reward. But since you don't know the maximum expected rewards, you need to learn the expected rewards of each and every arm, and then you try to pull the arm which has a max. So as you more number of times you pull the arm, you asymptotically reach to the maximum to the actual true values of the expected rewards. So yeah, so you have k arms. So let's say you have k. So let's say you have k arms. And then, so what you do is first play each arm once in UCB. So you play each arm once, and then I'll do some this thing. So first you have U star A. A belongs to the set 1 to K, or maybe I'll call it I because then again sets problem. So U star. So what this is the true expected reward the ith arm gives, and U star I is the calculated expected reward ith arm gives. I hope this is clear to everyone, because there were some doubts I think in the forum where people were asking the notation was not clear. So small q is the true value which you don't know. Capital Q is the as you go on doing your experiment, like you try to sample each and every arm, so you estimate the expected reward that an arm gives. So that is capital Q star I. And yeah, next okay, so play each arm once, and then after playing each arm once you have an Q star I. You have an estimate for each of the expected rewards. Then what you do is then you calculate the UCB UCB for each arm. This is given by Q star I plus square root of 2 into log n by ni. UCB at the nth step. Yeah, so what this gives you is, so previously in epsilon greedy, I think what you are trying to do is you are trying to just estimate this thing. You are estimating this with some probability you are exploring and with some probability you are not exploring. So now what you are doing is you are also looking at how many times have I, so what this term gives is, it tells you it's a like not a metric, it's a constant which it's a function which gives you how many times you have sampled down. The more times you have sampled down, the more true to its close value. So suppose you have sampled one time, its actual reward is say 1. Its actual reward is 1. But the instant you sample it, because it is random and it could have a caution, it gives you a reward of 10. And since you have sampled it once, it is very bad estimator of an expected reward. So what happens is you need to sample more this arm. So this gives you how many times you have sampled that arm, and the more the times you have sampled the arm, the better the confidence bound you have. So this gives you the better the confidence. Now what you're trying to do is you're trying to play the arm A, which gives you arc max of UCB, the arm you play at n. You're calculating the upper confidence bound of all. So what this gives you is, so suppose these are my arms. Okay, so 1, 2, 3, 4, 5. Let's say there are 5 arms, and yeah, you have the true values of the arm somewhere here. These are the true values of the arms. So what you want to do is you want to pick the 4th arm always, because 4th arm is the highest expected reward. These are the true values. But when you try to estimate, you estimate these values. These are your values that you have estimated. The red ones are your estimates, because you have sampled only a finite number of times, so not sampled asymptotically. The more you sample, the more closer you reach to the arm. So now the second term in the constant gives you that how close you are to the, so it gives you a bound on how close you are. So the more you sample, the shorter this confidence bound is. The less you sample, the bigger the confidence bound is. So yeah, so I hope the algorithm is clear. Is there any doubt with the algorithm? You guys have any doubt with the algorithm? Then feel free to ask.
Aniket, when you say UCB of I, you are essentially calculating the expected reward, right?
Okay, so maybe
On the
this,
left side of the
yeah,
board.
this is, maybe I just name it as a function. Maybe this is UCB1. I get the confusion because UCB, this is UCB1. So yeah, maybe I should name it a function. So this is a function. Yeah, I'm calculating your doubt here. Go ahead.
And so the U of I function is essentially giving us the expected reward of that arm I. Is that
Yes.
correct?
Yes.
Okay,
Expected
got it.
reward of
Okay.
that arm plus with what confidence you can say that that is my
Right.
exact value. So the more you
Yes, yes.
sample, so it's actually, as this increases, the whole value decreases. Ni is the number of times you've sampled the I
Yeah,
value.
got it. Thank you.
So more you sample, the more sure you are that the expected value, that this calculated expected value is closer to the real value. I hope that is clear.
Thank you. Thank you.
So are you guys comfortable with the theorem that sir has told in class? Do you want me to just go through it once through the theorem, or are you completely satisfied that using this algorithm will give you uh, yeah, will using this algorithm you will achieve the rate optimality that sir has told in class.
Can you shed some light on this Chernoff Hafting bound and where we can use the places where we can use it?
Okay,
Because
so
I see that it is being used in UCB.
uh-huh. And also yeah, it's
Yeah,
in
go ahead.
university.
Sorry.
Okay. Yeah, okay. So you want Chernoff of Dingbar. So let me do one thing. So let me just try to give you the whole theorem proof, like in short, really in short, and then while giving it, I'll give you how Hofding is used there. Is that fine with you? I will
Actually, if you can give some background on what this Chernoff Hafting bound is, that will be more useful
okay,
because
okay, okay, sure,
the
sure.
derivation of the proof is very nicely done by sir. It's just this bound. I'm trying to figure out what it is and where it comes from.
Okay, so Chernoff Hofding bound. I'll not confuse you more. I'll just write what sir has written, so what sir has taught in the class. So you have Sm greater than or equal to mu plus epsilon is less than or equal to or minus 2 epsilon square into, and also you have probability of Sm less than or equal to mu minus epsilon less than or equal to or minus 2 epsilon square. So what these two boils down as probability of Sm minus mu modulus greater than or equal to epsilon less than or equal to e power minus 2 epsilon square into n. Do you see this? Is this creative test? Like both the equations is, so you have how much above and below mi to mu. So what you have is okay. So you have x is a random variable. So first let me do it further. So x is a random variable whose support is 0 to 1. So x can take only values between 0 and 1. F can't take any more values. Okay, and then what you're sampling multiple from this distribution. So once you sample, you get x1, x2, and so on till xn. Since they're all sampled from the same thing, x1 also is random, x2 is also random, x3 also is random. So you get expectation of x1 is equal to expectation of x2 is equal to so on, expectation of xn is equal to mu, with 0 to 1 being the support of x. I hope that is also clear. So now, how do you estimate mu? So what you do is, if you have samples x1, x2, x3, up to xn, so what you do is, you add all those x1 plus x2 plus so on till xn by n. Yeah, so this is your Sn. This is your estimated mean. Pertaining it to the bandits, this is your estimated mean. Mu is your true mean, which you have no idea about. So now, what this gives you is, so probability of mod Sn minus mu. This term gives you how close you are to the mu. How close you are to the mu. So the probability of you not being epsilon close to mu is less than or equal to e power minus 2 epsilon square into n. It depends on n. So as you keep on, so let me draw it here. So suppose this is your true mean. This is your true mean. Okay, and you are estimating it to be, and okay, for estimating, someone is asking you, okay, how epsilon close are you to the original mean? Now you say that, okay, if I have taken n samples, the probability that I am epsilon close to the mu is always less than or equal to this quantity. As n increases, this quantity keeps on decreasing. So the more sample you get, the probability that your epsilon away from mu keeps on decreasing. I hope I am making it clear. And how do you get the Chernoff-Optic bound? That is whole another thing where you need to derive Hofding lemma. From the Hofding lemma, you need to use Markov inequality to do this. I'm not going to go through all of that. But do you want me to go through the proof of Chernow-Hofding lemma?
No, Aniket, that will complicate things.
Yeah, that will complement thing
Thank you.
because it basically has an Hofding lemma, which gives you some concentration bounds on how close you are to the actual mean when you start sampling, and then you use Markovity and Markov inequality to show that yeah. So I hope you can see that this thing, this inequality, the Chernow-Hofding inequality, is somewhat similar to a Markov inequality. I hope you are able to see that. So I hope you guys are familiar with Markov inequality also. So probability of x greater than a is less than or equal to expectation of x by a, where x is a positive random variable. So x has a 0 to infinity. Its support is 0 to infinity being. Yeah. So if x is a positive random variable, then this is the Markov inequality. Yeah. So all these concentration bounds, you'll get that they are the Markov inequality is the basic concentration equality. So probability that x greater than a is less than or equal to expectation of x by a. That is a basic. That is the starting point of where you start concentration equalities, where you try to see stuff where how close you are to the true things, and then building up on this, you go to Hofding inequality, you have Hofding lemma, you have Chernow-Hofding bounds, you have like multiple concentration bounds. So yeah, so I hope this is clear. So you guys don't want me to go through the proof for UCB lemma, right? Okay, so I'll just maybe I'll just state the UCB lemma once for you so that it's clear for you guys. Okay, so what do I have here is yeah, so for k greater than 1 and UCB, I use UCB with k arms. Where the distribution of all the arms has support between 0 and I, then the expected regret. Yeah, I think R was the reward. So let me write. Okay, I'll write expected regret. Expected regret is at most 8 summation I belongs to the set Q star I less than Q star K star log K by delta I plus 1 plus pi square by 3 summation j equal to 1 to k delta j. Yeah, so I think this is the regret that you get, and using this you actually get this constant, the constant that shows that how close you are to the original value. Okay, so this is the UCB lemma for regret optimality. So what this says you is if you go through with the UCB algorithm, then your expected regret would be always be less than this. So after UCB, I think Sir has gone through the back bounds for MLB, right? So back bounds he gave some complexity notions, and then I think Sir went to median elimination algorithm. So I'll quickly explain the median elimination algorithm. So yeah, if you guys have any doubt in that, you can ask me also. So
I have one doubt. Could you please clear the notations once there's a lot of confusion
yeah,
there?
sure. In the theorem for UCB, right? Apurva?
And in general,
Okay, in general.
particularly between Q.
Okay, so I hope this part is clear. That the small q is always for the true expected reward that an I gives. Capital Q is the calculated expected reward. So I think in the notation somewhere, Sir also introduced a timestamp for Q here, capital Q. So it gives at what time you're updating the expected reward. So small q is true expected reward, capital Q is calculate expected reward. Okay, and then okay, so notations I'll just go through. Arms 1 to k. Okay, and then small q star I is the true value. Capital Q star I at n, make it at time n, is equal to calculated or estimated mean reward of arm I, true reward of arm I. So here when I write small q star, so it means the true values. So in the theorem, when you're proving for small q, so it's like you know all the real values, but you're like, if I do the UCB algorithm where you're agnostic to small q's, you just use capital Q's, then also my regret would be less than this. I hope that thing is clear. While doing the proof, you use the true values to show that if I use an UCB algorithm, where in the UCB algorithm I don't know about capital Q values. I know I don't know about small q values. I know only capital Q values. Then that is what it is. And yeah, in the theorem delta I is equal to Q star I minus Q star A star. Or is it the other way around? It's Q star I minus Q star A star. Yeah. So Q star I is the original value for the I term. Q star A star is the Q star A star. It is the expected or true expected reward of optimal arm. So A star is the optimal arm. Optimal arm is the arm which has the greatest expected reward. So what you have is Q star A star is generally greater than or equal to Q star I for all I belongs to 1 to. Is this clear? Till now are the notations clear?
Yes, thank you so much.
Yeah, so in the case, yeah, go ahead.
Aniket, there was one more, right? Small q of I is also there. Like small q, not small q star, but just small q of I is also there. What does that represent?
Okay, could you? I think small q is small q star. I might be also have this thing, but yeah, you basically you have true value of the R and capital Q is estimated value of R. You have no other estimations of Q. It might be that in some places, or I might be wrong, or sir might have used Q star and Q this thing, but there is Q and there is capital Q. And there is a place where sir uses Q of Ni. This N denotes at which time instant you are actually calculating the expected reward. But once the whole algorithm is done and you have gotten an output, then all you'll get is capital Q star.
Nikhil, can you explain S, L, and M also?
Okay.
Notation.
In the theorem, right? In the theorem for UC. Okay. So before that, I think then maybe okay. Okay. So yeah. Who was it who asked it out just now? SLN in the theorem of UCB, right?
Right.
Yeah. Okay. Sure. So okay, then let me give all the notations that there are to be given in this. So okay. So PIN is the number of times ith arm has been played. In time n. Murali, do you still have a doubt on Q without the star?
No, Aniket. Yeah,
Okay.
that was clear. Thank you.
So yeah, this is the, now what you're trying to do is you're trying to find the expectation of Ti of n. This is the expected number of times you pull the arm I if you're using the UCB algorithm. So in the whole theorem, the underlying assumption is you're using the UCB algorithm. Everything you're doing, all the bounds that you're losing up is you're using the UCB algorithm. Okay. So expectation of EIN. This is expected number of times you are pulling arm I in n steps. And I hope you understand that this is random and where the randomness comes from. That is also, I'll just give you a hint. The randomness comes from the underlying distribution that each reward gets, because that is random. At the capital Q, the calculated expected average reward that you calculate, that is also going to be random. Since capital Q is random, the term u, the function u by the UCB algorithm, this function, this is also going to be random. Since this is going to be random, you are actually comparing all the u's of each and every arm. Since u itself is random, so the arm which is going to be the max argmax u, that is also going to be random. So you're always picking, so you're randomly picking arm at each time. So yeah, so the number of times you can pick the arm P is also random. I hope that is clear. Then you calculate expected reward, which is given by expectation of I of n into delta I, and I think you sum it over all I is equal to 1 to 3. I think this, yeah, if the optimal arm is there, then this goes to 0. Yeah, so these notations are clear, right? Okay, so now where did sir use S, L, and okay, I think sir in one of the steps introduced the notion IN is equal to I, or IA is equal to I. I'm not sure what notations are introduced, but this basically means indicator function of AN is equal to I. So this is an indicator function. I think I have told this in the last tutorial. So this gives you 1 when nth time you pull ith arm, and 0 if otherwise if other arm is pulled. So this is an indicator function. So this is what sir used in his notation also, and sir put this UCB this limit as CNS, which sir wanted to, because the theorem underlying assumes that you are following the UCB algorithm. So instead of every time writing the whole root 2 log n by number of times of this thing, so sir has just put a 2 log n by s. Now this s is actually number of times you have pulled the arm, but what is sir trying to do is, instead of, so s is a variable which plays the function of how many times you have pulled the arm. Now since this is random, number of times you have pulled the arm in time t, so you're trying to bound it with something, right? So the first thing you bound it with is L. So let me write it down. Expected EI of N is equal to 1 plus summation m is equal to k plus 1 to n, indicator I pulled the ith arm from k plus 1. Okay, does this step make sense to everyone? That till k I am round robinly pulling each and every one arm, and then after that from the k plus 1 step I am using UCB algorithm to pull my AN arm. So this gives you how many times I have pulled down. So sir bounds this by L plus summation m is equal to k plus 1 to n, indicator im is equal to I, and im minus 1 is greater than or equal to n. Okay, so what does this say? So this says that, okay, so expectation of TIN, that is a number. It is random, but it is a number. So it's a number. Sorry, TIN is random. Expectation of TIN is not random. Expectation of TIN is a number. So expectation of TIN, you are saying that, okay, it is at most L. Now, as you're counting, so as you're counting m is equal to k plus 1 to L, you check each and every time, because you know the formula. This is the formula for, okay, so you're counting. As you're counting each and every time, you're counting, did in my m minus 1th term, did I count till k, L? If I've counted till L, then only I'll add the event. Otherwise, I'll not add the event. So L is just like you're estimating it with an upper bound. So instead of 1, you're telling, okay, estimate, my estimate of expectation of number of times the arm N will be pulled is at most L. And once it's more than L, then I'll keep on counting the events where I get more than L. Does that make sense? What L is?
Yes, I got it. Thank you.
Yeah, okay. So,
So,
yeah.
excuse me. So, yeah, I wanted to ask that. So, at the end, we want this quantity to be low, right? So we don't want the indicator function to get 1, right?
Okay,
Do
could you just please repeat the question once again? Like,
so. The main thing is, at the end we want that the indicator function where you are using 1. Okay. So it should not be, the probability should not be 1, right? It should be 0, so that L does not increase much.
ha. Uh, 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 okay, I get your point that yes, you're correct.
Yeah.
You're correct in the case when I'm trying to estimate expectation of TIN. But I don't, like, I want to be as close to the expected value of TIN, but I'm just finding an upper bound. Like, I'm finding just the upper bound of expected value. I'm fine even if it goes more than L. I don't care about it.
Yes, yes, yes.
You're right. Like, while estimating, I want the second term to be as low as possible, so that
Yeah.
I get as close to it. You're right. But I don't like, since I'm just finding an upper bound of all my regret, I'm fine how loose it is. I don't care about how. So
We are losing gradually. Yeah.
yeah, we're losing gradually. We are losing it gradually. So it's like saying that 2 is greater than 3. Like 3 is an upper bound for 2, but then you are like, okay, if 2 is greater, if 3 is greater than 2, then 4 is also greater than 2. Like you're saying, like, that 3 is greater than 2. So then I'm going one more step, and so since I know that 3 is greater than 2, I'm also saying that 4 is also greater than 2. But the randomness comes here, and you need to look at all the events that can take place. So when fixing inequality, that is exactly what I'm trying to do. But when I'm trying to estimate it with something, I'm adding new terms and I'm expanding the event. Like I want to include more events in that, so I get a good closed form solution. The good closed form solution being this root 2 log n by n.
Right.
Okay, so
Ankit, I have a question.
yeah,
Yeah, see, this is regarding the TI of n and then the expectation of TI of n. So, as per definition, TI of n is the number of times you pull the arm I.
yeah,
When you are playing, say for n times, say if you are playing 100 times and arm I is pulled only 20 times,
yeah.
right? That means 20 times is what you are pulling the arm I, and how you are differentiating that in expected value of TI of n, that's what I'm not getting.
Yes, you are right. That's a very good question. So actually, that is what I wanted to make you guys clear, that there is an underlying randomness in everything that we are doing once you have given a UC value. So suppose, okay, let's do it. Let's do it together. So you have 2 arms. Okay, so you have 2 arms. Arm 1, arm 2. Both have some random distribution, underlying distribution with them.
That's for reward, right?
Yeah, that's for reward. That's for reward. Yeah. So I suppose this expectation is 10 and this expectation is 20. Okay. So I pull arm 1, I get 11. I pull arm 2, I get 9. Okay.
Okay.
So in the first time, okay, forget UCB. Let's do the basic vanilla. Let's do epsilon greedy or something. Okay. So 11, 9. what you want to pull now. You want to pull 1 or 2?
1, yeah.
1. Okay, so you'll pull 1 again. Now you get suppose 8. You don't pull 2, so you get 0. Okay, so this should be 0. And then I get 0. This step 1. This step. So step 1 I pull this thing. Step 2 I pull this thing. Step 3 I pulled 11. I got 8 and I got 0. Now you want to explore. So let's explore more. So this thing now we got 15 here. I got 0 here. Now this is all one sample path. Okay. So now I do some calculations and I see that okay, this mean is more, so I try to pull this arm more than this arm, and it goes on. Now there might be another sample path where the first time I pull 1, I get 5, but the first time I pull 2, I get 19. Then the third time I'll try to pull the second arm more. So the randomness in the rewards, and since what arm you are pulling next depends on what is your estimated reward.
Right.
So now each time I pull, I get a sample reward. That is random. Since that is random, this Q star I is random.
Right.
Since Q star I is random, the next time which arm has the maximum value of UCB is also random.
Okay.
So there is a probability with what next time. So there is randomness in what arm you pull next, depending on the experiment sample paths of the previous times. So you do the whole experiment one time, you get one sample path. You do the whole experiment one time, you get another sample path. Okay, maybe what I do is, okay, I'll show. I have a code for MCT basic epsilon gradient. I'll try to show it to you once.
Okay.
So yeah, maybe that will clear some of these doubts. But then I need to switch my switch it
Okay.
So you guys have any more doubts on theory part of it? So that I want to be done with this. We'll go to that, or do you want me to go ahead with the theory?
Aniket, sorry, one basic question.
Yeah.
This UCB1 and even PAC algorithm, right?
Yeah.
It's they call it as algorithm, but what are we actually coding? Like, where is the code
Yeah.
that will tell it we have to do root of 2 ln n by mi in ni and all?
No, this is the code. No, the algorithm is telling you to calculate this u function and see which is maximum, and then that is what you pull the next arm. You want to calculate this. The algorithm is so you have an environment. Okay, so you have an environment which has arms. In that environment, the environment knows like arm 1 has this much distribution, arm 2 has this much distribution, arm 3 has this much distribution, arm 4 has this much distribution. Now while you are coding up, you don't know what are the distributions. Okay, so what you do is, so first you pull arm 1 and you say that since the environment knows the distribution, it will give you a sample from that distribution, but the algorithm doesn't know. So now that you get that reward. Now based on that reward, you calculate this function, UNI function, UIN function, or UNI function, however you say it, UNI function. Yeah, UNI function, and then you compare with both the arms and you see which arm to pick next.
Okay, got it. Okay.
In the pack setting, you have a different calculation. I think the algorithm goes a bit different in the pack.
Right, yes.
Correct me if I'm wrong. There, what you do is you sample each and every arm for a particular amount of times depending on the number of arms you have and epsilon delta, because a pack notation has an epsilon delta. So I hope you understand the difference between the algorithms and even the median elimination algorithm. As time step goes on, you're shortening the worst arms. I don't think you might have, if you are not yet gone through median.
No, I haven't done median elimination yet. But this in the pack, right?
Yeah.
The algorithm says for each arm A less than capital A, sample A L times. Then L equal to there's an equation 2 by epsilon square. And all.
2 by epsilon square log 2k by delta.
Correct. Yeah. and then you say let QA be the average of the arm, and then end for loop. Output is argmax of QA.
Argmax of QA, yeah. So in pack, what it gives you is, what it tells you is, so I hope both the settings are, the algorithm settings are also clear with you. In UCB, you're trying to minimize the regret. That is what your upper bound is. The upper bound on the lower bound. The upper bound on the
On the regret, yes.
on the regret. And in pack, what you're trying to do is you're trying to find there was you're trying to find an upper bound, right? Upper bound on the probability that you are very far away from the actual. You're epsilon far away from the actual.
Right. Yeah.
Yeah.
With the probability delta.
Yeah, probability delta.
Yeah.
There, in the pack, the algorithm, you don't see an exploration exploitation dilemma, because all you're doing is you're sampling. The number of times you need to sample is fixed. Fixed matlab it depends on your epsilon and delta. So it says that if you want to be epsilon close to the true estimates, sample these many times each and every one of them. So that is basically in.
So Ankit, one question here. So are we going to find L? That is the minimum number of times we have to play to find out the best possible reward. Is that what the objective of pack bound is?
Okay, could you once again repeat the question? Yes, you are. In a way, you are right. You are right.
So I don't know how many times I have to play
Yes,
to find
yes,
out the upper
yes,
bound. So that is given by L, right? 2 by epsilon square Ln 2k
yes,
by
yes.
delta.
Yes, yes.
So if I find out the L, then I can play that many times to give a surety to the upper bound. I
Yes,
am
yes.
within epsilon,
Epsilon.
distance away from the mu.
Yes, yes, yes.
So is that the interpretation
Yeah,
of
that is
pack bound?
interpretation. That is the interpretation is exactly correct. That so what it says that suppose your epsilon is very high. So
Okay.
that L is equal to, let me write it down. So yeah, correct me if I am wrong. I think L is equal to epsilon by 2 by epsilon square into log 2k by
2k
delta.
by delta. Yeah.
Yeah, this is the thing, right? Okay. So now epsilon is the closeness here, delta is the upper bound of the probability that you have. So epsilon, if you increase epsilon, what happens?
L reduces.
So L reduces. So your confidence bound is the epsilon means how close you are to the less epsilon, the more close you are to the expected value. So as far away you are from the expected value, the L reduces. So number of samples to be very far from that is like very less. You want to decrease epsilon so that I'm close to the expected. As you decrease epsilon, the sample complexity goes up by L. Is that clear?
No, if you reduce epsilon, the value will increase, right? Epsilon is in the denominator.
Yeah, the
It won't
value will
decrease, it will increase.
Yeah, it will increase. As you reduce epsilon, L values increase. So
Correct.
what it is saying is, the more you want to go to the true value, the closer you want to go to the true value, the more number of samples you need to take.
Right,
So
okay.
practically you have a matching between both the things that you have got from the theorem and what you want to do actually.
Okay. So delta you cannot play around with, is it?
No,
Only
delta,
epsilon?
No, delta also you can play around with. Okay, but the interpretation is bit. I just have to think for 30 seconds. So, okay, what happens if you increase the delta? So, the log term inside decreases. Log is an increasing function, so the whole term decreases. L decreases. The probability. So, that is, I think this is the delta is the probability, the upper bound of the probability that you are so close to the delta. So you are fixing epsilon. The probability that your epsilon close depends on delta. How close you are probably. The higher the delta you have, the more number of samples you want. Is that? So if delta increases. Delta increases. Log k by delta delta is 1 minus delta. Was probability was bound to be 1 minus delta.
Right. Correct.
Yeah.
Optimal arm is probability is 1 minus delta.
Yeah, 1 minus delta. So you want delta to be as low as possible.
And this epsilon, when we say it is just some distance measure, is it like
Yeah.
Pythagorean or some
No, no, no.
Manhattan?
You no need to go into Pythagorean because everything is in reals.
What do you mean by that? I didn't get you, Aniket.
So the reward that you're getting is a scalar, not a vector.
Okay, okay. So it's just difference of the
It's
two.
just a difference.
Okay,
So
okay.
because rewards are scalar, you don't have to worry about Euclidean distance and Pythagorean distance and all this. It's just difference.
Got it. Thank you.
Sridhar, did I clear your doubt regarding the delta?
No. I just missed that 1 minus delta. See, 1 minus delta is what we require, is it?
So probability of
By definition, delta is something.
pack. Let's put it. Could anyone refresh me what pack is? I gave it to last class.
So optimal arm with probability 1 minus delta. That's what delta is.
Yes. So I want to decrease. So uh, I I want to decrease my delta in pack complexity, right?
Correct. Yes. So that you get the most probable optimal arm.
Most probable optimal, which is epsilon close to the optimal arm.
Yeah.
So
Okay.
so decreasing delta. So if I increase delta, I'm fine with less samples. But since I want to decrease delta, so 2k delta increases, log 2k by delta increases, number of samples increases. So more number of samples I need to pick so that I give you a higher probability that I'll be epsilon closer to the delta.
Okay. So both needs to be lower number, right? Epsilon and
Yeah.
delta, both.
I think someone also asked me why is it 1 minus delta, why is it not delta? I think you could do it with delta, then you'll get a 1 minus delta or some delta prime delta. You will comment, but yeah, you can do the theorem proof with just changing that small thing. It's not a big deal. But you need to verify that like intuition makes sense. And in pack we are not in pack we are not calculating the upper bound on expected regret. In pack we are only finding that the probability of me getting an arm which is epsilon close to the optimal arm has a probability of this much probability. And in UCB I don't want I don't want my output as the optimal arm. I just want I have an algorithm which says that I'll get the regret less than this, even while doing exploring and exploitation together. So let me do one thing. So I hope the theory questions are fine. So I'll just switch my
So Aniket, I have just a small question, right?
yeah.
So I was asking that in UCB, where are we considering the reward portion? At the end,
Okay,
it is
okay,
only
okay.
dependent on the sampling of arms. But if let's say there are four arms and each of them are sampled equal times, then how can we say that the algorithm will give different answers?
I didn't get you. Okay, could you just once again ask the question?
Yeah, so I was just asking that where are we considering uh, the meaning of reward term? So if we have got four arms, right,
Yes.
and each of the arms are sampled equal times,
Yes.
so how the UCB is considering and giving them different answers? How the UCB will give different answers? So
Uh,
2 ln ln n upon nj, okay.
uh-huh.
So and j is total number of sample from arm j.
Yeah, yeah.
So if arm one also got sampled four times, arm two also got sampled four
Huh,
times.
then it will depend on QJ.
Yeah. It will depend on qj
It will
only.
depend on QJ. Yeah.
Yeah.
But it will be QJ plus that confidence bound. So 4 times sampling gives you a confidence bound that you are this much close to the true value. So, and if you like look at it more clearly, it will be same, but yeah, that is where I think if you look at the theorem once, there you'll find that okay, is my screen visible?
Your screen is visible.
Okay, yeah. So it's like want to go to the true value in UCB. In UCB, it's you don't want to go to the true value of the optimal. You want to go to the true value of each and every one. In pack setting, what you want to do is you just want to find an arm which is epsilon close to optimal arm. I don't care whether it is the optimal arm or not.
Yes, and the for total regret also. For total regret, the bound is 8 ln n upon delta e square plus some convergence constant.
Yeah.
So, but it is considered in the proof only. It is not. It does not get significance in theorem.
But that comes up when you use UCB algorithm. So what the theorem
Yeah.
states is if you use the UCB algorithm, then your yeah, then your regret would be upper bounded by this. And then this is the term that you have. So if you change the confidence window there, the upper bound would change. Do you get my point?
Yeah.
So
Okay.
the variations that sir was telling in UCB is that you change the confidence window, the Q capital QJ plus the term, you change it and you get different upper bounds for.
Okay.
So you have different confidence levels for each other,
Yeah.
different upper bounds for regrets. So that is a variation that you have. I hope I'm clear.
So how did the authors came to know about the confidence window? I was just
Oh,
asking
okay.
for how did they approach for it?
This
It is
is
also
yeah. This is a very interesting question. This is the
yeah
whole point of research.
because
Okay.
because because sir also at some point he just substituted the confidence window,
Ha
right?
ha ha ha
So maybe I can screen share and
Yeah.
then
So
we can discuss.
that I think I'll answer this question not in this class, but I'll answer
Okay.
because that is a very important question. That's a very good
Yeah.
question.
Hmm.
I think yeah, I'll answer it in the next class. Okay, so
Okay.
that is a good question because the whole point of research is you trying to come up with that confidence bound. So what sir what I am showing you right now is okay. This is your algorithm. For this algorithm, this is my confidence bound.
Yeah.
Right? So how do I first know the confidence window that if I do this, then I'll get this.
Yes, because in the proof also,
Yes.
we are gradually loosening. That part is clear.
Yeah,
Okay.
yeah.
So like we have got L and we are adding a term, and then that term is gradually decreasing, or probability. Okay. But at that point when there are three claims where probability will get one or zero, in those claims are just substituted the confidence window, and
Yeah.
then he
Yes.
came to the at ln n and delta
Yes,
a square
yes.
result.
Yes.
Yeah. So
That confidence window also like intuitively if you want like how exactly they came up that I'm
intuitively, yeah, we can do
you
it.
can like you have a function which number of times you have sampled that arm if that increases then your confidence bound should
We have to
like
put it in Chernoff holding,
yeah.
and
So
then it will
then you have to
reduce.
yeah. So you have to use those concentration inequalities like instead of the theorem like you have to use concentration inequalities first
To the theorem, yeah, to
yeah
get to the result. We,
to
we,
get to the
we
result
first have
yeah
to do all that, then we can go.
yeah.
Sure, thanks.
Okay, okay, I hope my screen is visible, right?
Yes.
Yeah, it is visible.
Just let me just run the code. I'm not sure. Okay, this is taking a lot of time. Okay, yeah, I have one more information. Today, the 7 to 8, there was an 7 to 8 also there will be a tutorial session by another TA that was also posted, right? Today, that tutorial won't be there live, but the TA would upload like he would do the recorded session and he would upload. From next week, we'll be doing it Friday 7 to 8. Hello? Yeah, I hope that message is clear.
So every Friday there are going to be 2 sessions, is it?
Yeah, 2 sessions. So basically, we both will be covering the same concept. So, like, even if you come to my this thing and ask if there's a doubt, you don't need to edit that, or if you want, you can ask the second. Anything is fine. Like it's yours. 6 to 7 is my slot. So I'll do 1 hour of doubt clearing. 7 to 8 is the second.
Okay. Yeah, this session is very helpful so that we can interact and then get our doubts clarified.
Yeah. It's fine. It's fine. Yeah. So sometimes it also happens that maybe we both also are not so listening about your doubt. If you have doubt, we'll get to it in the next class. So the first one. Okay. So how many of you are comfortable with Python? Okay. Maybe screen hand raise or something maybe.
So I'm okay with Python.
So
Yeah, I am also okay.
So first thing you have to do is plotting. And then you define a class multi-arm magnet. So this is basically your environment. So every environment you have a mean and variance. So mean and variance for the arm. So mean and variance here I have taken it as a vector. So yeah, so these things I think you can code it up yourself. And then in the environment, also I am coding it up the estimate of each and everything and the number of times I have put. So in the last tutorial I give you a way to iteratively update the estimate just if you know the number of times it has pulled and the reward that has come up. So yeah, this is also one of the 2 of these things. And so I'm defining a function pull. So what does pull do is I get a reward every time I invoke the pull function. I get a reward from a okay, I've used NP random normal distribution here. That is simple, but I think UCB I should have a support of 0 to 1. Yeah, but yeah, it's fine. So I'll make the changes and all. But you could use uniform distribution here or any other distribution. And so reward you'll get that sample, and then you estimate that arm using the last time I have told you the estimate. So you know the previous estimate and the previous number of times it has been pulled, just add 1, and then the arms pulled also add 1, and you return the reward, the new reward. Yeah, this is the expected reward actually, so I written it as so next I have done the epsilon greedy. So this is epsilon greedy. So in epsilon greedy, yeah, so this is the this key is the probability of this thing. Like if it is less than epsilon, so this is probability of exploration and exploitation. So if it is less than epsilon, then you do exploration. So randomly any arm you pull. If it is greater than epsilon, then you do pick the max arm. This is the epsilon greedy. This is the UCB where you have the UCB criteria, estimate plus the square root of blah blah blah, and you return the arm max arm. So returning on the arm max arm and then you pull it. So these are some of the constraints means that I've given to justify this. Yeah, for the UCB, I think I should have not used Gaussian. I should have used some other random variable which has support 0 to 1. But yeah, I think it's fine. Then I'm actually using this. I'm updating the environment which I've created here. Okay, so then I'm just printing for check that all the means and slot machines and all are done. Okay, so this. So here you have. I'm calculating the average rewards and all for this is for epsilon greedy. So this is for epsilon greedy. Epsilon greedy, I'm doing it over multiple epsilons. So I recorded. Okay. So I hope you are able to see the blue one, 0. So could anyone say what epsilon equal to 0 would mean?
You are always picking the best term or whatever you found.
No, you are always picking the arm which I picked first.
There is no exploration, right?
Exploration, yeah. So you pick the k arms once and
continue to
continue to pick the best arm.
right.
So you see that the blue one is the highest one, is the worst. And as you increase epsilon, it comes down. I think since this is
The y-axis is regret, is it?
yeah, y-axis is regret. Yeah. No, yeah. Y-axis. Okay, maybe I should not show you this expected one. There was a good graph. So this is for. This is for UCB. UCB I need to use That's fine. Okay, this is for UCB. This UCB also I have, I think I used a variation of UCB. But I think you get the idea. I think now you can start coding up yourself. Like how to code it up is clear. Maybe I have made some mistakes in this code. I just coded this up.
And also the regret should minimize, right?
No, the regret would not minimize because regret I'm doing the cumulative regret. And what I'm plotting is the cumulative regret.
Okay.
So if I have regret at time 1 as 10, then 2 I would have 10 plus something. So
But 10 plus it will be less than 10, right? It will okay, it is you are adding cumulative regret, but somehow regret should minimize that. The optimization problem is the minimization of regret, I think.
Minimization of expected regret.
Yeah, minimization of expected regret. So why are we using cumulative regret here?
But here the epsilon 0 is showing the minimum regret.
No, that is the blue one. It's going high.
The blue one, yeah, blue one is showing the minimum regret.
No, it's.
But as you
it is maximum regret. Yeah, it's maximum regret.
Actually, epsilon 0 is showing the maximum regret, I think.
Yeah, epsilon is showing the maximum regret.
Okay.
Epsilon 0 is maximum regret. Okay, and then so eventually we are minimizing the regret. Yeah, here
so
also.
As you explore more, you'll try to minimize.
We are minimizing.
Since it's a random and I've not sampled over good number of things, so it's not this plot is not correct. What you would want to get is a sharp price and then straight line.
Yeah.
And I think I need to increase the number of times I'm doing this also.
Also, the reward function should be sampled in between 0 and 1. Right?
Yeah, that is also a point. For UCB.
For UCB, yeah. For UCB.
So if it is a straight line after some rise, then the interpretation could change, right? The reward area, the regret area, what you are seeing as a empty space on the top, above the characteristic, that should reduce, right?
No, it is not depend. It does not depend on the top. The triangle is the regret area.
That empty space on the top, right? That should reduce as you play with epsilon.
See, the cumulative reward, the first time, the cumulative regret, the regret would stay because you are exploring in the first. So you can't say that while exploring what I have done is just no more. So while exploring, you'll get a sharp rise, and once you've explored enough, you'll get a almost straight line. It will not be a straight line, it will be almost straight line. The almost straight line is that you're not exploring now. So regret. So the regret is actually expected reward for the optimal arm minus your calculated the calculated expected. Once they both are close enough, every time your regret would be 0, 0, 0, 0, 0. So cumulative reward would be, so it is like first instant if I get 10 regret, then 10 plus 5 plus 2 plus 0,
Yeah,
0, 0,
that's
0,
why.
0, 0, 0. So you get a rising curve and then no increasing curve, like a straight line. Does that make sense?
Is it like that, or asymptotically it will be trying to approach that optimal value, but it will never approach, right? There will be some decreasing values as you go. It won't be perfectly zero, right? Then
Okay,
it
okay.
becomes a
It will not be perfectly zero. It will not be perfectly zero.
yeah.
Like a straight line, matlab, I mean that you'll have almost similar straight line. It should be a like steep rise with change in slope and then almost straight line.
Okay.
Like because because you have variance, like it's all random. That straight line will have different.
Yeah, we are concerned about the slope. Maximally, we are concerned
Yeah,
about
yeah,
the slope, right?
yeah.
Slope should be more steeper
Yeah, so
to decrease the regret.
so now you guys can go back and so I think it will be very simple. Just set up a class for multi-arm minus, which is your environment. Give different distributions. I just started coding this up 1 hour before, so I might also have done some mistake, but I think you guys guess the gist of how to code it up. That was one of your doubts, right? So how to code it up. So code up an environment where you have all the true known values, the mean, the variance, and all define all the functions. Like when you pull a arm, you are randomly sampling from that thing, and how do you update the estimate without, you don't need to keep all the rewards in a vector. You just need to store the previous estimate and the number of times you estimate. These things will also be useful when you are doing the UCB part, because in UCB, when you're calculating the U function, you need number of times that each arm has been pulled. So these two things you do, and then you update your estimate at each time, update your number of times you have pulled, return the reward that you have gotten. Then define the epsilon greedy. Epsilon greedy, I think this is the round robin part. You can use for loop or any other loop that you see. So return random thing if probability is less than epsilon. If it is more than epsilon, then do the argmax of the maximum estimate that you have given. And this thing what it is, I did an uniform random distribution. If it is less than epsilon, then I'm exploring. If it's greater than epsilon, I'm exploring. Does this make sense?
Yes.
So then UCB also the same thing. Pull each and every arm one time, and then calculate the UCB criteria. And then return the UCB. Return those values for each and every arm, or for which arm you are doing. Then update this thing. Then give some values for your environment. Create an environment. Just check whether the environment has all the things that you want. Now, just do averaging. Just call it for one sample path and look at it. Just like, you can do whatever. I'll go back and check. This taking some time. If you guys want, you can wait till this is loaded. But I hope the coding part is also clear.
Yeah, we can try.
You guys can try. And in the next week, maybe you guys can come and tell me.
Sure.
Problems. You can try out, I think, what can you try out? Epsilon greedy with different values of epsilon. UCB, the vanilla one that Sir has said, UCB one, that you can try out. You can even try out the median estimation one. But median estimation one requires some more coding, because every time you need to create a list of arms that can be pulled. Okay, median estimation, some of you have stated that you have not yet gone through it. Okay, that's fine. But in median estimation, what you do is similar to CAP, you have suppose k arms. You pick all the arms some number of times, and then what you do is you cut half of it from the median. You remove the worst arms, and then you use the k by 2 ceiling function of k by 2 arms, and then again pull it some number of times, and then again you take the median, remove the arms, and then you take the best k by 4 arms. You continue doing that still until you have only one arm. That is median elimination. So you need to probably make a after making your environment, maybe you set up a function which says what are my active arms, and call the active arm function after each and every. This thing is not working. Sorry for that. Okay, so I don't think I have any more present. You are free to leave. And I just want to say that today's certificate session will not be there. The TA would be uploading a recorded session for this week. Next week he'll also be alive for he will also come for the live sessions.
Hello?
Yeah. If you have any doubts, you can ask.
Yeah, actually, one more thing, I actually missed the total session. Actually, I was under the impression that it's going to start from 7 p.m. So, can I get the recording of this?
This recording, I think the previous week's recording was shared by you by NPTEL, right?
Okay.
No,
And
I'm not sure. Was
I'm also not sure. I have to check.
Okay, I think NPTEL will share you the recording of this.
So will it be in the website, or we will get an email, Ankit? How will this be available to us? I don't remember seeing this in the NPTEL course site.
For 10,000 also is not good. Okay, so yeah, actually it is going. The slope is really decreasing. So if I didn't have this epsilon equal to 0, what we would see from the green ones are steep slope with Jainian slope very less. Here this part has a steep slope, which is very small. So exploration, this part is what you're exploring, and then you're exploring. So maybe I need to do the changes. Maybe instead of plotting for all the epsilons at once, maybe plot for just one epsilon. Yeah, I think okay, and the recording, right? Recording. You guys didn't find any NPTEL on the website, NPTEL website, like for the course.
Sir, I haven't checked that. Give me 5 minutes.